Hi, everyone. So I think we're going to get started now that we hit 35. And first of all, super excited to see everyone in the audience to finally get to talk about all the work that everyone's been doing in this domain. This workshop, funny enough, it was only supposed to be a single day, but two groups at the exact same time came up with the same ideas and had a completely different set of speakers. So it ended up being really fortuitous, and now we have this beautiful 2-day workshop with so many speakers from so many different parts of this domain. So I am really, really, really excited for all the talks. And hopefully, we're going to start with some opening remarks to kind of set the stage. But after that, our job is easy. We just get to sit around and enjoy all this amazing science. So Mehdi, who could not join us today, will be presenting the first part of this talk. And yeah, really happy to have him still here, even though he wasn't able to join in person today.
Yeah,
So Mehdi.
thank you, Cole. Thank you, Cole. Yeah, unfortunately, I wasn't able to join because of exciting things happening in the US, but I'm really excited for the workshop. We have an awesome lineup of speakers, and it's a really exciting field. So we thought of starting the day with kind of opening remarks, talking about kind of what Neuro-foundation model could possibly be, kind of the common trends in the field currently, as well as kind of the lessons that we can learn from language models and other models in other domains. So let's start with talking a bit about why potentially foundation models could be useful for neuroscience. Um, so the brain is a very complex system that allows us to perform very complex tasks, but this very complexity makes it really hard to understand. Typically, when we think about the traditional neuroscience experiment, where we have a hypothesis that we want to test, we collect a small amount of data from a specific brain region, so basically recording a few neurons at a time, but we're also having the individual perform a very specific task under very specific conditions. Basically, we're getting a narrow view of what's happening in the brain. And while we have made a lot of breakthroughs in understanding the brain using these type of approaches, we kind of want to see what else we could do to improve our understanding of the brain. And the current framework that we're using is one where a recording is basically a single small slice of the brain, as I said, along the spatial dimension, a few neurons at a time, and as well as along this task dimension, where we're only looking at the neural dynamics for a specific task. The question is whether we can slice together all these different, stitch together all these different slices to build a more complete picture of what's happening in the brain. And a potential answer to this could be a foundation model. So before we jump into what Neuro-foundation models are, let's talk more about the stitching idea. So one great example of this is the data from the International Brain Laboratory, which collected the same data under the same experiments across multiple labs and across multiple hundreds of animals. And what we're seeing here is a stitch of these recordings in the same brain for the same stimulus. So we're seeing the response of the brain globally as we stitch together the neural activity across hundreds of animals. And while this is possible for neural activity where we have very stereotyped behavior or stimulus, we want to see whether foundation models allow us to stitch together across much more dimensions and integrate across both task and context. So what is a foundation model? A foundation model is basically a general multi-purpose model that allows us to perform multiple different tasks. Historically, in language and in NLP, we've seen initially the emergence of these specialist models that were designed to perform one task at a time. So, for example, question answering or sentiment analysis, text summarization, etc. And usually are limited to a subdomain. So they would be specific to a language or specific to medicine or law or just more general knowledge databases. But what foundation models have shown is that if we move towards a large generalist model that is trained on all these on this large corpus of data sets, we can actually perform much better with this generalist approach. If I exaggerate the idea of stitching, we basically stitch together all these different data sets from these different subdomains and languages to create this large generalist model that performs really well. We see this trend also across other domains, including vision and speech, and more recently in graphs, as well as in biology, where we see this power of scale in achieving new state-of-the-art performance and unlocking new capabilities and new tools for performing different applications, and as well as new tools for doing science. So in addition to the fact that we want to stitch together all these recordings to get a more complete view of the brain, two other properties of foundation models that could be interesting are the following. So the first one is the power of scale, as I said. So with scale, we're able to, we've seen that models that previously weren't performing really well at certain tasks, at a certain scale for both model size and data size, we're seeing these emerging capabilities where the model is all of a sudden able to perform certain tasks. And this performance is only achieved through scale. And so one question that we can naturally ask ourselves is whether in neuroscience, limiting ourselves to low data regime training or models is limiting what we can accomplish and what we can understand from the brain. Maybe we need deeper and more complex models in order to actually understand what happens in the brain. And for that, we need much more or larger amounts of data. And the second property, which I think is really interesting, is this new framework in which we're now working. People now are able to, even non-experts are able to use language models and fine-tune them on their own data using small amounts of compute and minimal amounts of data. So we no longer need to be an expert in order to train a model on your own data sets, right? And so this framework of foundation models involves this large scale pre-training stage, which involves a lot of compute, a lot of data, but then it makes it way easier in the second stage for the fine-tuning, where you're able to make these tools more accessible and potentially unlock novel downstream applications by making these large foundation models happen in neuroscience. And so that's the second property that I think is really promising, and one of the reasons why we should explore Neuro-foundation models and their applications in neuroscience. So what is a Neuro-foundation model? I think we'll hear a lot from our speakers today and tomorrow. This is kind of one version or one view of what this could be. It kind of mimics this idea that we want to have a generalist model that performs multiple tasks. It can work for different types of modalities, including here in this talk, we're going to limit ourselves to spike in neural activity or calcium imaging data. But the idea is that it can be trained on data from different contexts where the individual is performing different types of tasks, including motor tasks and visual tasks, etc. And then it's a tool also that has multiple downstream applications. One of the most common ones that a lot of models focus on is BCI applications, where you want to decode some sort of behavior, but we can also see it extended to predicting something about the population of neurons that we're recording, including brain region or cell types, how and the neural dynamics across different contexts. One other interesting thing is that we're able to embed these different recordings into the same latent space, which then allows us to compare different neural recordings across a population or across contexts, which basically, all this to say is that these tools, this Neuro-foundation model could be used as a tool to perform different downstream tasks in neuroscience. Great. So as I mentioned, one of the main ones is this idea that we would have a BCI model that is trained on multiple subjects and for multiple tasks. The idea here is that we don't have to each time recalibrate the model or train a new model for each new subject and each new day, but that we were able to train a model that works for all these different animals under all these different contexts and behavioral tasks. Great. So in language, one of the things that we care about when we talk about scaling is basically typically the number of documents that we use to train a model. But the dimensions along which we're going to scale neural data is kind of more of an open question, and different work has made progress across these different dimensions. We have tried to identify in the spider plot what are the different potential dimensions of scaling that people have focused on in recent work, as well as potential future dimensions of scales that we can also work on. So this includes the number of subjects that the model is trained on, the number of recording time, but also the number of behavioral tasks that highlights the diversity of data that these models are being trained on. And so during this talk, we're going to try to kind of compare, as we talk about different models, what this spider plot looks like and kind of the progress that you have made in scaling across all these different dimensions. So yeah, we're going to now go through a few examples of recent approaches that builds towards Neuro-foundation models. We're going to not focus so much on the technical details of how these models work, but rather kind of highlight the main technical breakthroughs and the things that these models demonstrate in terms of scaling, as well as highlight the novel neuroscience applications and capabilities that are enabled by these approaches. So we'll start with Poyo, which is a paper from NeurIPS 2023. And it introduces a multi-animal decoder model trained specifically on cursor velocity decoding during motor tasks. And what this paper demonstrates is that scaling works. So this kind of was one of the big questions, is like, how can we actually train a single model on heterogeneous sources of data collected across multiple labs, across multiple animals, performing very different tasks. And what we find is that both the performance of, at least in decoding, improves as we scale the number of parameters of the model, as well as the amount of data that the model is trained on. The second interesting property that we can see here is the fine-tuning, which is, again, a really important tool when we think about neuroscience and how to make these foundation models accessible, is that these models can be very easily fine-tuned to new data sets while being computationally efficient, sample efficient, and parameter efficient. By only changing less than 1% of the model's parameters, we're able to adapt or calibrate this model on new data sets using only a few steps of training. The second follow-up work for this is Poyo Plus, which extends Poyo to enable it to perform multitask training across multiple animals performing different tasks. And so while the Poyo was trained on decoding cursor velocity, Poyo Plus can be trained on a wide range of tasks. And in this case, the model was trained on the Allen Brain Observatory calcium imaging data, where there are hundreds of mice performing or seeing this visual stimulus from different tasks, including artificial and natural stimuli. The model was trained with different with subjects where with recordings from different brain areas or visual brain areas, as well as different cell types. And one of the things that these models enable, in addition to scaling, is, for example, it enables us to embed all these recordings into the same latent space, which then allows us to compare and try to understand what's happening across these different populations of neurons in the visual cortex of mice. So this is another aspect of how we can see these large-scale models being useful as a tool for doing neuroscience analysis. The other interesting aspect, which kind of answers this question of whether there is this universal code that exists in the brain, one of the interesting experiments is transferring this model that was pre-trained on visual areas to recordings from hippocampus, recorded under very different contexts. And here again, we see that there is indeed an improvement in performance when we use this pre-trained model, suggesting that there is actually some universal code and an argument for being able to train a model on multiple brain regions and multiple behavioral tasks. Next call.
Awesome. Thanks, Mehdi, for the opening remarks. And yeah, I'm going to take over from here. So another really interesting method. So we've been kind of looking at how can we scale up neural decoding and capture that relationship between neural activity and behavior. But there are other ways to think about scaling approaches beyond, learning that relationship. So in this work here from Joel Yi et al. in NeurIPS 2023, there was a focus on how can we scale the prediction of neural activity in a self-supervised way. So imagine you have all this neural activity and you want to fill in the missing bits using masked modeling. This is what NDT did. And they showed that by pre-training broadly on multi-context data, they were able to fine-tune this model to do really well on new held-out animals in comparison to if you just trained a model from scratch. So this kind of highlights that there's a lot of diverse ways you could try to scale approaches. And we're seeing that, but what we're seeing converge across these approaches is that the scale really starts to matter, and it enables these new properties that we didn't think possible given, the deep learning models we had before. So this example here kind of highlights that there are more diverse ways to build these models as well. And I'm going to highlight, we have a couple more to highlight because I think it's really great to see the diversity of thought here. So there's really nice recent work focused on, instead of decoding or self-supervised learning, it focused on encoding. So how could we build a foundation model of responses from neurons? So this work from Wong et al. focused on building a foundation model of the visual cortex and looked at responses of these optophysiological responses from 135,000 neurons of mice watching movies. And they showed in this amazing work that if you pre-train on animals that are watching this movie, you're able to not only generalize to novel stimuli that we're not trained on, but also are able to generalize to new animals that were not part of the training. And so new stimulus domains, new animals, and also you're able to dig into this model and look at what it's learning. For example, can you use it to predict anatomically defined cell types of excitatory neurons and other data sets like the microns data set? So not only are we looking at decoding and self-supervised learning now, we're also looking at neural encoding and how does the outside world get encoded in the responses of the visual cortex. And for the last model, we're going to talk about another interesting way of thinking about self-supervised learning. So before we kind of thought about like infilling parts of the recording and understanding, the structure of what's missing, but we also could think about the structure of neural recordings across multi-region rich data sets. So for example, this work, multitask masking, focused on self-supervised method for learning both temporal, causal, and region level structure from international brain laboratory data sets where you can record from many regions broadly of mice performing the exact same task. So in this work, by alternating between different masking schemes, like masking out neurons, or masking out future time steps, or masking out full regions, the model was able to learn how to predict across these different spatial temporal scales. And again, what is shared across these works is the power of scale, because when this model was trained across 34 mice doing the same task, we found that you could basically see a big improvement in performance across all the different metrics that were being evaluated, with interregion prediction, forward prediction, and even behavioral decoding. So all of these works kind of highlight the same thing, but they're doing it in very different ways. And now we want to start to look at where is the field going, right? So these were all different models doing different things, but you can start to really compare and contrast them using both the spider plot that Mehdi showed before, but also laying it out on this exponential graph. You can see that the number of hours used to train these models have actually been increasing almost exponentially over the past few years. What started with 10, 20 to 30 hours is rapidly scaled up to thousands of hours of neural recording for training these models. And it's not just the number of hours that have changed, it's also the size of these models. Just like in language modeling, where you see this relationship between the model size and data, we too see this in Neuro-foundation modeling, where we have these model sizes that we can scale over time. And again, it seems to be exponential, the rate at which we're building these models and the size of these models. So it's really exciting to see that this field, while new and so much to be done, there's already this kind of exponential growth we would hope to see in this large scale kind of modeling setup. And again, we're kind of excited to see like all these things were developed in kind of in their own place, in like their own silo, but you can start to compare and contrast what are the dimensions of scaling that each of these approaches have looked at, right? So a lot of these methods have really started to scale on the number of subjects, the number of neurons, the recording time. But there's other axes that we really haven't started to explore yet. For example, the number of behavioral tasks, where even at the most complex data set that he's been trained on, it's a couple of behavioral tasks at a time, at most. So what we need to see and what we hope to see in the future is that we can grow the dimensionalities of scaling, and we can start to think about how do we encompass all the variability that the brain has beyond just multi-animal recordings. And to do that, it's really going to depend on the data. So while we've been focusing on the models, you can actually think about this approach of dimensions of scaling on the data sets. So here we have a couple exemplar large data sets, but there's so much data out there living on archives that could contribute to our understanding of this variability. But here we have the International Brain Laboratory Brain-Wide Map, which really has tons of brain region diversity. But as I mentioned before, right, the behavioral diversity, it's a single task that's being performed across all these mice, is more limited. And then you have all this amazing data from the Allen Institute, both ePhys and OPhys, and the Sensorium data set, which has so many units that we can take a look at the encoding of. And then last but not least, you can actually think about scaling as a function of many different data sets. So if you look at Dandy and you think about the number of subjects, the number of units, the number of behavioral tasks that lives there, there's actually so much on the table when it comes to scaling and how much we can do with these models. So one thing I want to shout out, I think it's really important to highlight, we focused on models and data, but there's more to this story because Neuro-foundation models will require a really solid technical stack. I came way from the spike sorting literature where the ecosystem really got fragmented over many decades, and it was very hard for there to be a consensus on what to do or how to compare them or anything, right? And this is still a young field, so I think there's a lot of hope for building a solid technical stack that we can share across labs and try to really have all of these different things together. So the data, how we preprocess, how we pose, estimate, how we spike sort, how we build software to actually create these models and share these models, and then the models kind of live at the top of that technical stack. And I want to plug some recent efforts to kind of build a community of foundation modeling because it's really important that we all share the same language, both in how we talk about foundation models, but also in how we code and how we compare foundation models. And since I'm starting to run low on time, I'm just going to hop right ahead to what is probably the most important part of all, which is the benchmarking, right? So we have these models, we have this data, we have this software, but we haven't yet been able to really all be in the same place. And no better way to do that than benchmarks. So I want to shout out this really amazing benchmark, the Falcon benchmark, which focuses on adaptation at a few shot. So if you can pre-train broadly across many different data sets or monkey data sets or mice data sets, and then adapt to new species and new tasks like reach or finger movements of a monkey or songbird vocalization, right? These are going to be the questions everyone wants to ask, and we need to answer these in a shared place. And again, another benchmark that's coming soon is focused on how do we scale this to many different brain areas and many different mice doing the same task. So the IBL brain-wide map is creating a benchmark to try to actually put all these foundation models in the same place to understand how much information about behavior or future neural dynamics like forecasting is in the mouse brain, and how can we bring these models together to kind of benchmark this in a shared space. So Mehdi, I'm going to let you take the last slide because I think this is a really beautiful slide that kind of talks about the whole field.
Thank you, Cole. So as Cole was describing with this pyramid that we're looking at for the technical stack, all this work is enabled by all this foundation where we're able to use this open data, we're able to use these tools that help us process neural data and as well as behavioral data. And so it's good to, in the context of this workshop as well, to highlight how this is a multidisciplinary field. It's not just about scaling and deep learning. We're going to see like foundation model builders focused on designing these scalable models for neural data, focus on developing this infrastructure needed for scale, which is a big challenge. But we also have machine learning experts, which kind of answer this question of how these models could be used as tools to do neuroscience and science in general. So things like fine-tuning and knowledge distillation for real-time practical applications. We also have computational neuroscientists, which have a lot of important insights that could be used to improve the design of these models and improve the way we evaluate and benchmark these data sets, as well as propose hypotheses and use these tools for training for helping us train, know what the domain knowledge is to train these models. And finally, experimentalists giving us collecting data sets and giving us these experiments that we can train these models on. But I think this is not just a pyramid where it's actually a cycle where even these foundation models, we could see it in the future being given to neuroscientists and experimentalists and see what types of questions they're trying to ask. And there needs to be this feedback loop where we learn about the different challenges that exist in neuroscience and how these tools could help improve the way we do explore how the brain works or improve the way we do BCI, etc. So yeah, this is a really exciting field, and this workshop, I hope, will be a great way of seeing this in interdisciplinarity in action. We have a great lineup of speakers that are going to talk about these different aspects of these models, both in terms of Neuro-foundation models, the datasets that are going to be used for scaling, as well as in general large-scale theory behind large-scale neural analysis. This is our schedule for the day. We're going to have multiple talks from our speakers. We're going to have 5 minutes after each talk for questions. And then we'll end the day with a panel discussion, talk about more about the current state of Neuro-Foundation models and where we see it going.